Welcome to this video on demystifying convolution. It is the mathematical engine powering modern signal processing, AI, and engineering. Convolution fundamentally combines two signals to produce a third, distinct output. It's a structural blending of two sequences or waves over time, where the shape of one function is modified by another. To calculate convolution, you reverse the filter, slide it continuously past the input signal, and calculate the total overlapping area at every time step. This reveals their overlap over time. The core flip and slide operation adapts to various data types, leading to continuous, discrete linear, and discrete circular convolution. Continuous convolution analyzes physical waves and analog systems. The formula involves an integral, calculating the total overlapping area of the static input signal and the flipped and sliding filter. Discrete linear convolution is the standard for non-periodic digital data. The output array's length expands because the filter slides completely past the input, causing partial overlaps at the edges. Discrete circular convolution handles periodic signals by wrapping data around a loop using modulo arithmetic. The output length does not expand. It remains the maximum of the input and filter lengths. Choosing the right discrete method depends on the required output length, edge behavior, and primary use case. Linear convolution represents physical phenomena, while circular is used for the discrete Fourier transform. The convolution theorem offers a computational shortcut. Convolution in the time domain becomes simple multiplication in the frequency domain, using the Fast Fourier Transform. Small numeric kernels dictate massive transformations. Examples include moving average for smoothing, edge detection, Gaussian for noise reduction, and differentiation for detecting curvature. Convolution has key mathematical properties: commutativity, associativity, distributivity, and identity. These properties govern how the operation interacts with other functions and signals. Convolution is the invisible backbone of modern applications, including image processing, audio simulation, signal filtering, and calculating probability density functions. For linear time invariant LTI systems, if you know the impulse response, you can use convolution to predict exactly how the system will react to any input. Our tool bridges abstract mathematics and practical calculation. It provides comprehensive engines, flexible inputs, interactive visualizations, and transparent step-by-step math. Stop calculating by hand and start visualizing the overlap. Master the concept, architecture, and action of convolution using the interactive solver at MiniWebtool.com/convolution-calculator.